Have you ever wondered where everything came from? The answer might be a little more complex than you'd think. Welcome, dear listener, to the fascinating world of cosmology, where we'll explore the Big Bang Theory, a scientific explanation for the origin of the universe. Picture a singular point, a moment in the distant past, around 13.8 billion years ago. From this singularity, everything we know, every star, every galaxy, every atom in your body sprang into existence. This is the core premise of the Big Bang Theory. But the Big Bang was not a typical explosion. It was an expansion, an unfurling of space and time itself. To understand this, imagine a loaf of raisin bread dough. As it bakes, it expands, and the raisins move away from each other, just like galaxies in our ever-expanding universe. Now, what's the evidence for such a monumental claim? Well, we have two key observations. First, the cosmic microwave background radiation, a faint glow permeating all of space, a relic of the universe's hot, dense infancy. This radiation was first detected in 1965 and has been studied extensively ever since. Second, the redshift of galaxies. When we look at distant galaxies, we observe that their light is shifted towards the red end of the spectrum, indicating they are moving away from us. This redshift, first noted by Edwin Hubble, provides evidence that the universe is expanding. So, the Big Bang Theory posits that the universe began as a singularity, a point of infinite density and temperature, and has been expanding ever since. It's a theory supported by multiple lines of evidence, from the cosmic microwave background radiation to the redshift of galaxies. The Big Bang Theory provides the most compelling explanation for the origin of our universe. But as with any scientific theory, it's not without its mysteries and challenges. As we continue our journey, we'll delve deeper into these enigmatic aspects and explore the ongoing quest to understand the universe's past, present, and future. But who first proposed this groundbreaking idea? Our story begins in the early 20th century with the inspiring contributions of several key scientists. Among them, one name stands out: Georges Lemaitre, a Belgian physicist and Roman Catholic priest. Lemaitre is often credited as the father of the Big Bang Theory, as he was the first to propose in the 1920s that the universe is expanding from a single, primeval atom, an idea he daringly called the hypothesis of the primeval atom. But the theory didn't gain traction until another key figure entered the scene: Edwin Hubble. Hubble, an American astronomer, made an astonishing discovery in the late 1920s. He observed that galaxies were moving away from us in all directions, a phenomenon now known as Hubble's law. Hubble's observations provided empirical evidence supporting Lemaitre's theory of an expanding universe, giving the Big Bang Theory its first solid footing. Yet the theory was still in its infancy, lacking a comprehensive explanation of how the universe evolved after the initial explosion. Enter George Gamow, a theoretical physicist and cosmologist in the mid-20th century. Gamow and his colleagues proposed the concept of nucleosynthesis, explaining how the universe's lightest elements, hydrogen and helium, were created in the hot, dense early universe. This was a major step towards the detailed and nuanced Big Bang Theory we know today. Despite initial skepticism, these groundbreaking ideas gradually gained acceptance in the scientific community. The Big Bang Theory began to take shape, transforming from a radical hypothesis to a widely accepted explanation of the universe's origins. It's important to note that these scientists didn't work in isolation, but built on each other's work, making significant strides in understanding the cosmos. The Big Bang Theory, as we know it today, is the result of the collective efforts of these remarkable scientists. Their pioneering work laid the foundation for our current understanding of the universe, setting the stage for future discoveries and advancements in cosmology. Let's delve a little deeper into the science behind the Big Bang. This wasn't just an explosion in space, but rather a rapid expansion of space itself. This concept is known as inflation, a phase of exponential growth that occurred in the first tiny fraction of a second after the Big Bang. Inflation explains why the universe appears flat, homogeneous, and isotropic, with matter and energy evenly distributed throughout. Next, let's talk about nucleosynthesis. This is the process by which the first atomic nuclei formed in the early universe. In the immediate aftermath of the Big Bang, the universe was a hot, dense plasma of quarks and gluons. As it expanded and cooled, these elementary particles combined to form protons and neutrons. Eventually, these atomic nuclei began to combine, forming the light elements, hydrogen, helium, and traces of lithium and beryllium. This process is known as Big Bang nucleosynthesis, and it was complete within the first 20 minutes of the universe's existence. Now, on to one of the biggest mysteries of our universe, dark matter and dark energy. Despite its name, dark matter is not dark in the sense that it absorbs or emits light. Instead, it is dark because it does not interact with electromagnetic radiation, making it essentially invisible. Yet it's believed to make up about 25% of the universe. Then there's dark energy, a mysterious force that is accelerating the universe's expansion. It's estimated to account for nearly 70% of the universe's total energy content. These are just some of the fundamental physics concepts that underpin the Big Bang theory. Each one has been meticulously studied and rigorously tested, contributing to our understanding of the universe's origin and evolution. So, when we talk about the Big Bang, we're not just discussing an abstract idea. We're delving into the intricacies of the physical laws that govern our universe. The Big Bang theory is not just a theory, but a comprehensive model backed by complex physics. Are there any other theories that challenge the Big Bang? The question many of you have been waiting for. Let's dive right in. The Big Bang theory, as we've discussed, is the predominant cosmological model for the observable universe's origin. But it's not the only player on the field. Enter the steady-state theory and the cyclic universe theory, two alternative theories that offer a different take on how our universe came into being. The steady-state theory, proposed in the mid-20th century by Hermann Bondi, Thomas Gold, and Fred Hoyle, suggests that the universe doesn't evolve or change with time. Instead, it maintains a constant density, with new matter continuously created to maintain this equilibrium as the universe expands. While this theory elegantly explains the universe's uniformity, it struggles to account for the cosmic microwave background radiation, a key observational evidence supporting the Big Bang theory. On the other end of the spectrum, we've got the cyclic universe theory. This concept posits that the universe undergoes infinite cycles of big bangs and big crunches, with each cycle lasting trillions of years. Though it's a fascinating concept, one that elegantly addresses questions about what came before the Big Bang, it's yet to provide a comprehensive explanation for the observed acceleration in the universe's expansion. Now let's put these theories head-to-head with the Big Bang theory. While the Big Bang theory isn't without its challenges, it's got a strong backing of observational evidence, from the cosmic microwave background radiation to the redshift of galaxies. In contrast, the steady-state theory and the cyclic universe theory, while intellectually stimulating, lack the same level of empirical support. However, it's worth noting that these alternative theories have played crucial roles in advancing our understanding of the universe. They've pushed us to ask more questions, to seek more evidence, and to continually test the boundaries of our knowledge. Despite the merits of these alternative theories, the Big Bang theory remains the most accepted model for the origin of our universe. What evidence do we have to support the Big Bang theory? This question has driven scientists to great lengths, and several key pieces of observational evidence have been found. Two notable examples are the Planck and WMAP satellites, both of which have made substantial contributions to our understanding of the universe's early days. The Planck satellite, launched in 2009 by the European Space Agency, mapped the cosmic microwave background radiation, or CMB, with unprecedented precision. This radiation is a relic from the universe's infancy, a sort of cosmic baby picture, if you will. Planck's measurements have provided strong support for the Big Bang theory, confirming several of its key predictions. Meanwhile, the WMAP satellite, which stands for Wilkinson Microwave Anisotropy Probe, spent over 9 years studying the CMB. Its observations have helped to determine the age of the universe, the density of atoms and dark matter, and even the curvature of space itself. Like Planck, WMAP's findings are consistent with the Big Bang theory. However, as compelling as this evidence may be, it's important to acknowledge the limitations of our current data. For instance, both Planck and WMAP have observed anomalies in the CMB that aren't easily explained by the standard Big Bang model. These include the so-called cold spot, an unusually large and cold region of the sky, and the axis of evil, a strange alignment of temperature fluctuations in the CMB. Furthermore, the Big Bang theory leaves several big questions unanswered. What caused the Big Bang in the first place? What is the nature of dark matter and dark energy, which together make up about 95% of the universe? And what, if anything, lies beyond the observable universe? Ongoing research is tackling these questions head-on. Scientists are developing new experiments, building more powerful telescopes, and proposing innovative theoretical models. Despite the challenges, the quest for knowledge continues. While the Big Bang theory has strong evidential support, there are still many mysteries left to unravel. What implications does the Big Bang theory have? And what does the future of this theory look like? The Big Bang theory, the prevailing cosmological model of the universe's origin, has implications that ripple through various fields of study and even into our daily lives. It has not only given us a scientific explanation for the genesis of the universe, but also sparked profound philosophical and theological debates. It challenges us to ponder questions of existence, causality, and the nature of time and space. Is our universe one of many? What existed before the Big Bang, if anything at all? These are questions that continue to confound the most brilliant minds and fuel ongoing discourse. The theory has also significantly impacted various scientific fields. For instance, in physics, the Big Bang theory has driven research into areas such as quantum gravity and string theory. It has pushed astronomers to continually refine their techniques and technologies, propelling advancements in telescopic technology and space exploration. Speaking of future directions, the recent launch of the James Webb Space Telescope is expected to revolutionize our understanding of the universe. This state-of-the-art observatory will peer back over 13 billion years to see the first stars and galaxies forming out of the darkness of the early universe. Such advancements are set to provide us with even more information about the Big Bang and the early universe. Moreover, ongoing research into cosmic microwave background polarization could potentially provide further evidence of the inflationary period of the Big Bang. This would be a monumental step in confirming this critical aspect of the theory. And so, the Big Bang theory continues to evolve, driven by new discoveries and technological advancements. It inspires us to ask bigger questions, to push the boundaries of what we know, and to continually seek answers about our universe's origin, evolution, and eventual fate. The Big Bang theory continues to shape our understanding of the universe and drives future research in cosmology. So, what have we learned about the Big Bang theory? We've journeyed from the theory's inception through the depths of the physics that support it, to the evidence and its implications. And now we circle back to revisit the main points. At its core, the Big Bang theory is the scientific explanation for the birth of our universe. It proposes that everything started from a single, incredibly hot and dense point, around 13.8 billion years ago. From this singularity, the universe expanded and cooled, leading to the formation of atoms, stars, galaxies, and everything we see around us today. Key observations, like the redshift of galaxies and the cosmic microwave background radiation, provide robust evidence for this theory. The redshift shows us that galaxies are moving away from us, implying an expanding universe, while the cosmic microwave background radiation is the afterglow of the Big Bang itself, still detectable today. We also delved into the contributions of notable scientists like Georges Lemaitre, Edwin Hubble, and George Gamow, whose work has been instrumental in shaping and refining the Big Bang theory. Their research and discoveries have helped us understand complex concepts like inflation, nucleosynthesis, and the mysterious dark matter and dark energy. We touched upon alternative theories, such as the steady state or cyclic universe models. While these theories have their merits, they struggle to explain the observational evidence as comprehensively as the Big Bang theory. However, it's important to remember that science is a continual process of discovery and refinement. While the Big Bang theory is currently the best model we have, it's not without its limitations and unanswered questions. Ongoing research and future technological advancements, like the James Webb Space Telescope, will help us probe deeper into the universe's past and refine our current understanding. The Big Bang theory, though still evolving, stands strong as our best explanation for the origins of our universe. The pursuit of knowledge is unending, and as we continue to explore and question, we come closer to understanding our place in this vast cosmos.